Hello, this is the second part of the chapter 1.7, and today we'll talk a little bit more about linear independence and how graphically distinguish linear dependent and linear independent vectors. First, let's start from the definition. Last time we learned that if we have a set of vectors, we can form what's called linear dependence relations by taking a linear combination of vectors by arbitrary weights x and set it equals 0. And in this case, if solution exists, it can be a trivial solution or all our weights x is equal 0. And in this case, we say that our vectors are linear independent, or at least one of the axes would be non-zero. And in this case, we say that this is a non-trivial solution and our vectors are linearly dependent. So how do we can use this definition to visually or graphically distinguish between the vectors? Let's just start on from the R1 and build our case to multidimensional space. Okay, let's look at R1, which is the simplest case of one vector, say, which can be linear dependent or independent on itself. So equation in this case will be x1 v1 is equal 0. And if our vector v is non-equal 0, then the only way to get the solution of x1 v1 is equal 0 is if our x is actually 0, or if we have the system can have only a trivial solution. And by definition, this means that our vector, non-zero vector, is linearly independent of itself. So what if our vector is non-zero? In this case, then any x would give us 0 on the right-hand side. So in this case, the only possible solution is non-trivial solution. And by definition, this means that our system is linear dependent. So basically, we can say that only 0 vector is dependent on itself. Any vector of non-zero length will be the independent of itself. Okay, let's build up our case and move to R2. And this case, our linear dependence relation will be x1 v1 plus x2 v2 is equal 0. And there is a really nice theorem in the chapter 1.7, which I really strongly recommend you to work through, which tell us that the set of two vectors is linearly dependent if at least one of the vector is the multiple of each other. So since we know that the vectors which lies on the same line is the multiple of each other, we can easily visually recognize this dependence. We can also say that the dependent vectors have the same span because span refers to all sets of linear combinations. And the linear combination is just multiplication by number in two-dimensional case. And any two vectors which do not lie on the same line will be by default independent. Okay, let's move up one dimension to R2. And in this case, if we have a dependent vectors, they always will lie in the same plane. And again, we can use the definition of span and say that the set of linearly dependent vectors will have the same span, or we can use the definition of linear combinations and say that dependent vectors, one of the dependence vectors will be equal of a linear combinations of two others. And independent vectors does not lie in the same plane. And we can build up our case in the higher dimension And again, theorem 7 summarized, it's really nicely in test, and say that if we have two or more vectors which are linearly dependent, that happens if and only if one vector form the linear combination of others. So that will be similar to our three-dimensional plane, but that would be much harder to sketch. Okay, this is the summary of geometrical interpretation. And now I would like you to go back to the chapter 1.7, read through the rest materials, and try to work through several examples of linear dependence and independence.